Anushka, and today I'm going to walk you through an exciting and very important project that is brain tumor detection using deep learning. So, this project is not only relevant to for the academic purposes but also highlights that how machine learning and image processing can be applied in the medical field to assist with the early diagnosis and potentially lives. So, in this video, I'll explain the overall idea of the project, the steps in all from data pre-processing, feature extraction, classification, and then we'll go through the code and the result. So here you can see this is the code. uh, the Google Colab is there. Here I just imported all the Python libraries which is required. Then we'll quickly jump to the this part. Okay, so here there are some useful Python functions are there that helps us analyze the image data set, especially when working on the machine learning or the deep learning process. So here we can import the module. The two function definitions are there, this path and the title. So the path to the dataset folder and the title, which is either training or the testing purposes. Then initial setup is there, then looping is there, it's very important. Then there is a function is written for filter the images. Then the function is for print the image count. And finally we use the matplot library to create the single row figure. Each class gets its own subplot that shows one example image along with the class name as the title. So we can also turn off the access to make it look cleaner. So now there are some function calls are there, and now you can see the results here. So this is the simple but powerful way to get the quick overview of your image dataset. So these are the images from the training dataset, and these are from the testing dataset. You can see the clearly. Now we'll quickly jump to how to load the training and the test dataset. So this is the code for that. Here the function overviews like a get data generator. Okay, this is basically for pre-processing. Then we use the data augmentation for training and validation, and here we use the Keras image data generator, this one data generator. So here what happens, first of all, the training data generator also includes the validation split and of 20%. So that means 80% will be used for training and 20% will be set aside for the validation. Then we are using the test data generator. Then the training generator. For training generator we are flow from the directory like here. So image are resized to fit the model's input size, for example 224 by 224. This is all happens behind the scenes, so just understand this. The labels are one hot coded and we shuffle the data for better performance. Okay, then validation generator is there, test generator is there, return statement is there, and yeah, that's it. With just a few lines of code we have set up the complete pipeline to load and pre-process our dataset efficiently. Now we'll jump to the next part, that is build model using the transfer learning. See, this is the code for that. We define the function called build model here. Okay, so its job is to custom image classification model on the top of pre-trained network. Like we are using the three base model here, which is the 16 ResNet 50 and the DesNet 121. So we have to first pre-train the base model. Then we have to set up some the most important thing is that we are set the include top is equal to false here. See, this line is there. Okay, so because we don't need the original classifier, we will be adding our own for the brain tumor classification task. After completing this, we are freeze the base model layers. Then we add the custom classification layers. So there are three layers are there. First we apply the global average pooling. Then we add the dense layer with 121 units and the ReLU activation function to learn the complex model. Then we are doing the dropout of 0.4 rate is there. Then final output layer is there. Then we combine base and the custom layers and compile the model, and yeah, that's it. Then we can evaluate the model. So for evaluation, just the function overview. The function takes the three inputs, that is train model, test model, and get the true labels, get the model prediction, get the class label, everything is there. And we can see the classification report also. I'll show you later. The print input is there, the confusion, we can display the confusion matrix also. This is the confusion matrix, and that's how we can evaluate the model. Then now, this is the heart, this is the prediction. So this is the heart of our code. It's very important, this part. So first of all, what's the happen, we pull the three things, that is true label, class label names like glioma and no tumor, and file path for each the test image. Okay, so as I mentioned above, there are four classes there. Glioma in the first part, like for training, glioma, meningioma, no tumor, and pituitary. Right? These are the four classes in all. So now this is all the code written for the prediction. So predict land probabilities are there, convert them to class, then finding the correct and the wrong prediction. We can separate the correct and incorrect prediction using the numpy. Then looping files are there, then plotting the correct predictions, and everything is there. Okay, so then we define the model configuration. Then the epochs are there. See, you can see the epochs models we want to test. Transfer learning with multiple CNN architecture is there. So each key is the name of the model we want to evaluate, the VGG16 ResNet. Each tuple that include the pre-trained model class from Keras and the pre-processing function that prepare the image format specific model. So this is the structure for that. You can see the pre-processing functions are model specific setting for the that means for the comparative experiments, train the multiple models. And yeah, lastly, yeah, we'll run each of this model through the training evaluation, with the training evaluation and visualization, and find out which one is the most accurate for our classification task. So make sure to stick around, the results may surprise you. So these are the results for one. We will see the results one by one for each model. So this is the result you can see for VGG16. Here you can found 4571 images. They are belonging to train dataset. Then 1141 found, they are belonging to validation, and 1311 they are belonging to the test. And the 50 epochs are there. You can see the results of that. All the epochs result are given here. These are all the result for this data set. So this is something that training runs we are using. So we can initially accuracy is quite low, like only 12.5% is there, but by epoch 5 accuracy reached to 81.1%. see here. And then for epoch 15 it's 90%, and then if we jump to the 25 epochs, then it's almost 93%. So clearly VGG16 learns to generalize very well, looks like at the classification report. So these are some graphs are there for VGG16 accuracy models, and this is for loss. This is the classification report, and we can see the final result is 0.88%. This is the best performance, overall accuracy. Best performance is showing the no tumor, which shows you 0.96% F1 score. And then possibly the lower performance we can see for meningioma class, which shows 0.75%, possibly due to overlap with the glioma less distinctive features. So this is the confusion matrix. This is the diagonal. So diagonal shows the correct prediction of the class. The upper and the lower side of the diagonals, they are the wrong predictions of the model. You can see here the correct prediction of VGG16 and incorrect prediction of VGG16. Now we'll jump to the next model results, that is ResNet model. So for this one, the 57.7% accuracy, and for the epoch 5 already reached to 91. See here 91, and it just took the 18 second. And final test result, you can see the graphs here for ResNet model. And then for the classification report, the accuracy is 0.88%. We can say it is the same for VGG16 model. So strong performance again with the high recall in the no tumor class, and just like VGG16, a little confusion between glioma and meningioma. This is the confusion matrix. Now you can see the correct prediction and incorrect prediction of this model. Now we'll quickly jump to the density model. So for density model, you can see from it is started from 41.9%. Then for epoch 10, it's almost reached to 91% here for epoch 10. Then test accuracy is around 82 to 85% for the epoch 12. You can see here. And then these are the results. So basically you can see the confusion matrix, it's 0.87% is there. Like means loss consistency drop showing the good coverage, but though detailed classification matrix when showing here visually and numerically data set model perform comparably to VGG16 and ResNet 50 with slightly better learning curve early on. To summarize, all three models perform well for brain tumor classification. VGG16 and ResNet both achieved the 88% test accuracy, and this ResNet model came very close with the similar performance and potentially the better coverage early on. This is the confusion matrix. Again, we are showing the correct predictions and the incorrect prediction is there. And this is the comparison of the test accuracy across the model. So you can see this is the result for ResNet 50, VGG16 and ResNet 121. The highest result is ResNet 50. Then we'll see the next part here. So this is the graph which shows training accuracy of the different deep learning model using matplot. So you can see this graph. What are the results of this graph? Training accuracy comparison across the model. You can see the results here. These are all pretty clear. Then you can see the results for validation accuracy comparison across model. Then this is the training loss comparison model across. This is the training loss comparison across the model. And in conclusion, all the three models perform well with the test accuracy around 88%, but ResNet 50 fastest, convince and slightly better generalization, VGG16 stable and reliable through slower to learn, and ResNet 121 comparative performance excellent feature reuse. So if you are training on a limited data, VGG16 or ResNet may be your best bet, but while DenseNet 121 can excel with more epochs and tuning. Thank you.